And last time we learned about optimization in the relative sense, in that we found local min or max. And they're also called relative min or max. And now we're going to think about the absolute sense, where we're getting the global min or max. In some sense, global extremum are harder to find, but they're also easier to find, and you'll see that why in a moment. And in fact, you already know this from Calc 1. So we need to find all the points of interest. And in Calc 1, we found critical points and also boundary points. Here is the theorem that says if we have a nice function on a nice domain, then we have min and max, and they occur either at critical points in the interior or on the boundary. That's the same situation as we were in Calc 1, where we found critical points inside, and we always have to test boundary points because those might not come out of our calculations, but they could be the biggest. You can look at the other worksheet from last time, and we saw an example of that. So the harder part is that we have to treat two cases, both interior and on the boundary. The easier part is we don't need any first or second derivative tests. When we found out we have a finite number of numbers to check, and the biggest is the max and the smallest is the min. That's it. Right, so that the second step will be the classifying part will be easy. Right, so let's find all the parts when we have to do both interior and exterior. So let's look at this one. This function on that domain. Let me look at interior first. So I think interior is a little easier. Interior. To find critical points in the interior, we would take partial derivatives. F sub x is equal to 2x minus 1. F sub y is equal to 6y. So that means critical points. We have, well, if those, and then we set those to 0, right? So then we know y is 0 and x is half. So we have 1/2 0. And since we need it later, we might as well calculate that now. F of 1/2 0 is equal to 0, 1/2, 1/4 minus 1/2 is negative 1/4. That's our value. So that's it. Oh, by the way, is this in the interior? Yeah, this region is x squared plus y squared less than or equal to 1. If we plug that in, well, we get indeed inside this region. Okay, so that's the interior. So that was easy enough. But we also have to think about the boundary. The critical point occur either at critical points or on the boundary. The boundary looks like a circle. This is the circle x squared plus y squared equals to 1. And we would like to find the max on this circle. And how do we do that? Well, if x squared plus y squared equal to 1, we can rewrite this function and make it simpler. Right? So the function is x comma y equals x squared plus 3y squared minus x. But y squared is equal to y minus x squared on the boundary. We're only caring about the boundary right now. If we're on the boundary, then we have that expression. So we can simplify this and get x squared plus 3 times y minus x squared minus x. Notice that this is now a single variable situation. And also, let me call this g of x. Just give it a name. It's a single variable function. I would like its value is exactly the same as f of x comma y, and I would like to know what is the min and max of that. So let me clean this up a bit. So this is negative 2x squared minus x plus 3. And we also know that x is between -1 and 1. All right, over here is a circle of radius 1. So we have this new optimization problem, but this is a Calc 1 optimization problem, and you already know how to do that, right? So we've reduced a 2-variable problem to a 1-variable problem. So by now, then, what you need to do is the new thing is done. The only reason why this problem is hard is just it's long. You have to keep going, right? But you already know how to do this. How do I find the min and max of that single variable function? Well, take the derivative, find the critical points. So that is the derivative. So then if g prime of x is equal to 0, then that means x is equal to 1/4, -1/4. And so then I can see that this is a critical point. So g of -1/4, this gives me, I have to plug it in here. Oh, 25/8. I hope I did that right. We also have to calculate g of 1 and g of -1, right? Because those are potential places that have the min or max for g. So g of 1 should be easy. Add up all the coefficients, so that's 0. G of -1 means this one is negative, it's positive, no, that's 2. So notice that if you're looking only at g, then this one is big and this one is small. Yeah, on the boundary, g equals to 1, that is a minimum, a global minimum for this function g of x. Right? So don't forget the boundaries of the single variable function. Right? X doesn't go from -infinity to infinity, it only goes from -1 to 1. And in fact, at 1, we get the smallest value that g could possibly take on. However, this 0 is still bigger than this -1/4. Okay, so this -1/4 is the minimum, and then I can't get both of them. Oh, I can do this, and then this one is the max. So we identify min and max. Notice that at the last step, classification is very easy because you just know which numbers are biggest, which numbers are smallest. You don't need to use first derivative tests. You don't need to use second derivative tests. And then this 2 is nobody. It's between 25/8 and 0. This 0 is a minimum on the boundary, but in the interior, there's something that's even smaller than that boundary point right there. All right. So that's it for today. Constraint optimization. This is the idea is very simple. The execution takes a little bit of time, and this interior part is the same as what we learned last time with relative global min or local min or max, except we don't have to use second derivative tests, so that's easy. The boundary is the tricky part, okay, and you can see that if the boundary looks complicated, this substitution in here will get messy. And next time we're going to see a better way of, maybe not a better way, but a different way that we can approach this boundary problem. Right? So remember, we already learned how to find optimization, to optimize in the interior, and today we had to do both interior and boundary. Next time we're going to focus on boundary and learn another way to do that. Okay? So that's it for today. Bye.